All right, well, let's begin. The homework assignment is due now, and the lab calculations and mini report are due today in lab, 2 o'clock and 3 o'clock, depending on the lab group assignments. And your next homework assignment is going to be due on Tuesday the 17th. So that's a week from today for homework 3A. There's going to be 3 assignments within Chapter 3. Homework 3A, 3B, and 3C. So this is the first set. And we're going to work a lot of examples in class today. You should probably be able to solve almost all of those problems after the material that we cover in class today. So you can get a head start on that. Any questions related to the announcements?
That's for our edition of the book, right?
What?
That's for our edition of the book, right?
Yeah. Yeah, I think that we got that nonsense all sorted out. Yeah. I hope so. We do. I won't say I hope so. I'll say that we do. Okay, well, last time we talked about the hydrostatic equation. We looked at it a couple of different ways. We looked at where we could say the pressure at some location divided by gamma plus the elevation at that location is equal to the pressure at some other place divided by gamma plus Z2. And the way that we applied that hydrostatic equation was by looking at a tank of water where a invisible triangle was floating just above the water surface to indicate that it's in contact with the air. And there's these little invisible lines indicating the water ripples, so reinforcing the fact that it's in contact with the air. And what that means is that if the air pressure is 101.325 kilopascals relative to the vacuum of space, then the water pressure right there is the same. Now that only makes sense if you think about it, that that the water pressure is going to be exactly the same as the air pressure where they touch, because what else would the water pressure be other than the pressure of, it's not like it would jump up instantly just 1 millimeter under the surface. But an important thing to just keep in mind is that the pressure of the water is equal to the air pressure at the interface where the two touch. So the way we use this version of the hydrostatic equation is that we'd pick some location. Let's say we could let this be location 1, and then we had some other location, and then a datum. What's a datum? Is datum? No, I'm not going to make a joke, a pun. Pun's the lowest form of humor. Datum. Okay. So what is that?
It's a reference point.
All right. Very good. It's a reference point against which we're measuring elevation. All right. So if we know that there's some distance up to the water surface, since we selected location 1 as the water surface, then that would be Z1. And what is the gauge pressure of the air right there? Very good. Remember, the difference between absolute pressure and gauge pressure is that when we talk about gauge pressure, we're saying that it's relative to atmospheric. And so right at the water surface, the pressure at 1 relative to gauge is 0. Okay, so we'd have some Z1, and then at 2 we would have a Z2 that would be given, the distance above the datum to location 2, and so that then we could find P2 by rearranging this equation. We'd rearrange it to be P1 divided by gamma, and that turns out to be 0 since it is atmospheric pressure. And so then we would just simply have Z1 minus Z2 and multiply that by gamma. So I rearranged this to solve for P2. That's sort of like the full hydrostatic equation. But then towards the end of class, we introduced the idea that a change in pressure, delta P, is gamma, unit weight of water, multiplied by delta H. And this looks very similar to that. where we just have Z1 minus Z2. All right, that's the delta H between the 2 points. Between point 1 and point 2, that is delta H. So we have delta H representing the difference in the elevations, and gamma being the unit weight of the water. What is gamma, the typical gamma for water? 9810, and the units? Good, newtons per meter cubed. That might even be on a quiz sometime, if a quiz was headed your way. All right. So, let's calculate, just as a review, at a depth of 35 meters, what's the absolute pressure and the gauge pressure at location 2, and using both approaches to calculate what is the pressure at location 2. All right, so this is one of those cases where it's absolutely fine, in fact encouraged, for you to collaborate with the people sitting next to you to calculate the pressure at 2. And when we say absolute pressure, that's assuming that this location is at sea level, where the atmospheric pressure is 101,325 kilopascals. And so pressure of the atmosphere in this example is going to be 101,325 newtons per meter squared. All right? So, hop to it. Go ahead and calculate the pressure. Yeah. Excuse me? Yeah. Thank you. That's right. Yeah, it's a plus sign. Thanks for noticing. All right, so in this example, what we were trying to do is compare, just to make sure that you get the same answer, either by the full hydrostatic equation or by just keeping track of the change in pressure. And so also looking at what is the pressure in an absolute basis versus a relative basis. And so absolute pressure assumes that atmospheric is 101,325 newtons per meter squared, so that the pressure at 2 is going to be the pressure at 1 plus the increased pressure that comes from going 50 meters above the datum to 15 meters above the datum. So 50 minus 15 is 35 meters of depth that we have gone down through. The pressure, therefore, is going to be increasing. In terms of gauge, of course, we're assuming that the pressure at 1 is 0, and then the pressure increases because we've gone from an elevation of 50 down to an elevation of 15 through fluid, where gamma, you should remember that gamma is a rate. Gamma, the unit weight of water, tells you how quickly the pressure is increasing as you go downward through the fluid. So every 1 meter of water that you go down, the pressure has increased 9810 pascals, or 9810 newtons per meter squared, for every 1 meter of elevation you go down through. Any questions about that example? Well, even if you're going down through 2 different fluids, pressure is additive. It's just that we have to consider that accumulating pressure in steps. So let's say that we've got a tank of 2 different liquids. There's water and oil. And because the oil is less dense than water, it's floating on top. In this illustration, it says in the problem statement that the specific gravity of the oil is 0.75. So specific gravity, sometimes we abbreviate it with the abbreviation SG. What does it tell us about the oil? If the SG is 0.75, what does that tell us about the oil? What is SG? Specific gravity. Good. Exactly right. It's the ratio of density of, in this case, oil relative to the density of water. So 0.75 means that the density is going to be less than water. In fact, since the density of water is 1,000, just by knowing that the specific gravity of the oil is 0.75, we know that the density of the oil is 750 kilograms per cubic meter. Yeah, I can do that math in my head. 1,000 times 0.75, all right? So also, we can know that it can be the unit weight relative to the unit weight of water. And so in this case, we could calculate the oil's gamma. It's going to be 0.75 times 9810 newtons per meter cubed. I can't do that math in my head. Dr. McCormick can. That guy's amazing when it comes to doing math in his head. Not me, though. All right, so in this case, the oil will be 7357.5 newtons per meter cubed. That's the unit weight of the oil. Everybody comfortable with that or have a question about what to make of specific gravity? Just as a preliminary step. Well, let's get the dimensions on this drawing. Just so that nobody falls into the trap that I constructed. I've constructed a little trap. You got to get wise to these traps because whether it's a quiz question or a test or the FE, which you'll be taking probably, you'll be taking the FE exam about like 16 months from now, roughly. So it says that there's a layer of 1.1 meters and then the total liquid level in the tank is 4 meters. So 4 meters is the total liquid level here. And we want to know what is the gauge pressure at the bottom of the tank. So down here, what's the pressure? Okay, so the obvious mistake you don't want to make is to say that you're going down 1.1 meter and then going down another 4 meters. All right? All right. So what we know is that this distance between this layer and the bottom of the tank is 2.9 meters, is the distance down from the interface of the oil and the water. Oil, water, and the oil was what had the unit weight of 7357.5. And the water, 9810 newtons per meter cubed. Okay. So pressure is additive. You have a homework problem that basically is just based on this same exact idea, pressure being additive. So the pressure at the bottom of the tank. We can split this up into points. Let's say here's location 1, here's location 2, and then we're going to call this location 3 at the bottom of the tank. So the pressure at 1 in gauge. Remember, well, it's not shown there. I'll show it now. Here's a triangle. It's implied by the fact that the tank walls continue up. It's implied that that's in contact with the atmosphere, that that oil layer, the top interface, is in contact with atmosphere. And so what will be the pressure at 1, Elman? Here at the top of the oil, in terms of gauge. Same as the air, exactly right. So what's the gauge pressure of air? If you have a tire gauge, right, the tire gauge that's not connected to the tire, that's just sitting in your hand, it's going to say 0 because it's measuring the air pressure relative to the air pressure. So pressure at 1 is 0 in terms of gauge. Pressure at 2 will be delta H times gamma. Okay. The delta H is going to be the distance between 1 and 2, 1.1 meters. And then the gamma that we're talking about is the gamma of the fluid that we're going through. Yeah, there is water someplace, but between 1 and 2, the fluid is oil. So we'll put in the unit weight of the oil, 7357.5 newtons per meter cubed. Okay, so the total pressure at 2, 8093.25 pascals. And then the pressure at 3 is going to be the pressure at 2 plus delta H times gamma. So pressure is additive. And we didn't go all the way from 1 to 3 because it's 2 different fluids that you're going through. I suppose you could come up with some sort of a weird weighted average of what's like the average unit weight of the fluid, but let's not do that. Let's just do it the right way. Okay. So it would be 8093.25 pascals plus the unit, the distance of 2.9 meters through a fluid of water. So we have the 9810 newtons per meter cubed. And that increased pressure, that increase is going to be another 28,449 newtons per meter squared. And so the total pressure at 3, when we combine the 8,093 and the 28,449, they have the same units. Pascals, remember, is the same thing as newtons per meter squared. So the total pressure, 36,542 pascals. The homework problem you have that goes along these lines tries to throw a little curveball at you. And I'm going to let you swing at that curveball. I'm not going to try and break it down for you. But just remember that you have to break it up into steps. Don't go through 2 different fluids in one step. Always put an intermediate point at the interface between 2 fluids. Yeah?
So, like if you had some crazy thing where you had multiple fluids, you could
Yeah.
just continue down doing the same thing.
Good question. Yep, you absolutely could. So if you had, for example, oil on top of water, on top of mercury, and you wanted to know, let's say, what's the pressure, like you've got a tap here. This is a water cooler. You know, this is a football game, and it's like a hilarious prank you're pulling. And the players are going to be drinking mercury for a little while anyway, but then they'll get this delicious fresh water, and they'll think, oh, the worst is over. We've drank all the mercury. Now it's water from here on out. But then they get the oil later, like in the 4th quarter. It's just, you're sitting up in the stands laughing and laughing. So before that, if you wanted to know what's, you know, like how quickly the water is going to go out depends on the pressure here, then you just go 1, 2, 3, and then 4. So pressure is additive, which was your original question. And I've just recorded myself talking about poisoning the football team. You know, the thing is that mercury, yeah, I am going to put it on YouTube. Mercury isn't by itself poisonous. It's only poisonous when it is methylated, something like that. I don't know. But yeah, it's really dangerous. It's funny, the mechanical engineering candidate that was here visiting campus yesterday was talking about how he used to play with mercury as a child. Like, I don't know if any of you were in that presentation, but kind of funny. All right, well, let's move away from just calculating the pressure and talk about how pressure can be made to perform work. Maybe some of you have been to a garage before and seen how easily they're able to lift up cars using hydraulic press. And so consider the case that we want to transmit pressure. And the way that this works is that there's an air compressor, not pictured, an air compressor that's taking the atmosphere and putting it through this tube, and so that in the head space above the oil, in a container, when you've got a liquid and then a gas above it, that gas above it is called the head space. So here we have a pressurized head space, and the air pressure is pushing down on the oil. All right, so we've got a lot of pressure in here, and it's pushing down on the oil. And so in this case, we wouldn't say that the pressure right here is 0. The pressure would be whatever the gauge is reading at the control valve, or whatever we set up the pressure to be on the compressor. Okay, so the pressure is pushing on the oil, and then what happens as we go down through a fluid? How does the pressure change? Okay, so the pressure is going up. The pressure is going up. What about when we go sideways through a fluid? How does the pressure change when we go sideways through a fluid? There's no change in pressure as we go sideways. Okay, so the pressure was big. It got a little bit bigger because we went deeper. And we went sideways, and it's the same pressure. And then as we go up, the pressure is decreasing. And it looks like that these two are about the same. So we can assume that whatever pressure is inside the air tank, that's also the pressure that's pushing up right here on this metal cylinder. This is like a big solid metal cylinder, 25 centimeter diameter. And the oil is pushing up on that cylinder. And there's a formula here. It says force is pressure times area. Okay. In the problem statement, it says that for this big metal cylinder being 25 centimeter diameter, I've already calculated the cross-sectional area of that using area is pi d squared divided by 4. The area of this is known to be 0.04909 meters squared. Okay, and we pressurized the air in the tank to 600 kilonewtons per square meter. So that's the air inside the tank. Pressure is 600 kilonewtons per meter squared, and we assume that that's a gauge pressure. You know how I told you that by default, if you have no other information, to just assume that the density of water is 1,000. It's only when I tell you the temperature that you should go look up to find the exact density. Well, by default, pressures, when I give you pressures, are going to be gauge pressures. The exception will be when it needs to be absolute, or when I tell you that it's an absolute pressure. So it'll just be like a gas law problem, or cavitation problem, vapor pressure. Those are the rare instances where pressures will need to be in absolute terms. But more typically, like here when it says the air pressure is 600 kilonewtons per square meter, and that says that they've pressurized this tank to be 600 kilonewtons per square meter above the atmosphere that surrounds that tank. So that's the gauge pressure, not an absolute. Yep, yep, it will. So what Andrew's just noticed is, so when this starts to move up, then the pressure is going to be decreasing, right? So what if it was oil all the way up to here? Well, that means that the pressure, instead of being equal to what it was there, it's actually going to be a little bit lower. And that's why eventually it stops raising. Is, what causes it to raise and fall is how much pressure is inside of the tank, and also it'll get into equilibrium. It'll rise until it stops rising because there's an equilibrium between the force of the car acting down and the force applied on this, the circular cylinder, since force is pressure times area. Okay, so in this example, what is the force of the car if what we know is the pressure and the cross-sectional area? We know the pressure of the liquid and the cross-sectional area of the cylinder. Well, all we have to do is multiply the two together. The force acting upward is going to be equal to the force of the car acting down. This is in equilibrium, and so the forces are equal. The force is going to be pressure times area. So 600,000 newtons per meter squared, and the cross-sectional area of the cylinder is 0.04909 meters squared, is equal to 29,454 newtons. That's the force that is being transmitted upward by the oil onto the cylinder, and that's the combined force of the cylinder and the car acting downward on the oil. This is a way of transmitting pressure to, to perform work. What's the weight? What's the mass of the car? Calculate the mass of the car. About 3,000 kilograms. So it's probably a BMW or like a car from the 70s or something. It's really heavy. 3,000 kilograms, that's like 6,000 pounds. It's pretty heavy. It's got gold in the trunk. How could we get this to lift more? There's two ways I can think of. A bigger tank. Now that's an interesting question. How would a bigger tank do that? Okay. It turns out that how big the tank is and how much oil you have, that doesn't matter. But you're on the right track. Nope. Think about the formula. The force that it can lift is equal to the pressure and the area. Because it was the area of the cylinder that mattered. Interestingly enough, it's not the area of the tank. The tank could be narrow or wide. It doesn't matter. It's the cylinder that has to be big. And so one thing you could do is increase the area of the cylinder, or we could have gotten a stronger compressor that will make it pressurize above 600 kPa. So now it's in equilibrium right now. If we turn the compressor on and it goes above 600 kilonewtons per square meter, then that'll cause this to rise. And it won't rise forever. Let's say if we turn it on to, instead of 600, let's see, do we know what the liquid is? Oil. Let's just assume that this oil is 7,000 newtons per meter squared. And so what if we increased the pressure inside of the tank by 7,000 pascals cubed? 7,000 newtons per meter cubed, we're assuming is the unit weight of the oil. So if instead of 600 kilonewtons per square meter, what if it was 607 kilonewtons per square meter? Well, then what would happen is it would rise 1 meter. And then it would come into equilibrium and it would stop rising, because remember, the pressure decreases as you go up. And so, you know, the cylinder interface would be higher than it was, so it would rise until the cylinder interface was at a location where the pressure in the area is equal to the weight of the car and cylinder above it.
Wouldn't the pressure increase inside the cylinder?
If you increase the pressure here, then it will increase at the same elevation, but then it would cause the cylinder to rise, and then it decreases because you'd still be going up through oil.
I was thinking there was air inside
Above the oil?
the... Yeah.
Yeah, it's just metal. Yeah, metal. This is metal in contact with the oil. Yeah, it's a solid metal cylinder.
What's the point of using oil? Why can't you just use air the whole time?
Because air is compressible, and I think in this case you need something that's non-compressible. You could use air, but I think the reason why they choose oil instead of air is they want a liquid that's non-compressible. Good question. Okay, here's a hydraulic jack. Now it is transmitting pressure and it's amplifying the ability to perform work. There's actually a couple of different ways that you're able to lift something heavy with this jack. The first, if you think back to statics, remember that moments allow you to increase a force that's applied. Think about the handle on this thing. You've got a handle that's pivoting around a point. Here's a handle. Okay, here's the pin. So if you push down 33 centimeters from the pin, and then as you push down, you're causing this little cylinder here to get pushed down. But if you're considering just the bar itself, what it's doing is that this cylinder is going to be pushing up there, and the moment distance there is 3 centimeters. And so one way to magnify your ability to transmit force is with a lever. And so this is just like with what happens with a crowbar. You know, if you've got a bar and you're trying to break open a safe door, you want a really long bar so you can grab the end of the bar and you're pulling on the bar, and then down at the safe it's just moving a few millimeters to gouge the metal before you can open up the safe. But the same thing is happening here, where you're amplifying the force. And so if you push down at F with 100 newtons, then that 100 newtons, it's going to be more than 100 newtons that's being applied over this area. So that's the first way that you're able to lift something really heavy at 2, is that the handle itself is magnifying the force. But then the other thing is look at the difference in the areas. We've got a difference, an increased area at 2, and so that's going to be amplifying the force as well. So let's go through and do the calculations on this one and see how much that jack could actually support. The first part of it, the moment part, is that we've got 100 newtons being applied at a distance 33 centimeters from the pivoting pin, and that's going to cause the force at B, I'm going to call it. The force at B, and that is at a distance of 3 centimeters. And so therefore the force at B is 1100 newtons. What's the pressure inside of the jack? There's probably a hydraulic fluid in the jack. How can we find out what is the pressure, the liquid pressure inside that jack? Good, right. So remembering that force is pressure times area. If we want to know the pressure at this fluid, it's going to be the force divided by the area. And so 11,000 newtons is the force that this little plunger is pushing on the fluid with. And the diameter that's given there, we need to calculate the area at 1. It's going to be pi d1 squared divided by 4. And that area is known to be 0.00017773 meters squared. That's for the diameter of 1.5 centimeter. So D1 is 0.015 meters. So let's divide by the area. 0.00017773 meters squared. That gives a pressure of 6,225,000 newtons per meter squared. That's the pressure of the fluid. What if, instead of 2 centimeters in diameter, what if it had been, what if 1.5? What if it was 2 centimeters in diameter? What would have happened to the fluid pressure if that was a bigger plunger? How would that have changed it, Elin? How would the pressure inside here, right now it's at basically 6.2 megapascals because we had a certain force that was applied in a certain area. What if we had increased the area? What if it was a bigger diameter cylinder there? It would decrease the pressure, right? It would, if we had a bigger area, then the pressure would be lower. So what we want to do is we want to have as small an area as possible because we want a lot of pressure in there. Probably the limiting factor is what kind of pressure can the seals handle? You know, like if the pressure is too high inside here, then the oil is going to start leaking around the seals, and that's what happens. I've got a hydraulic log splitter that I bought from Harbor Freight. So you know it's like the highest quality equipment possible, right? Yeah, it was $100 at Harbor Freight, and it does a great job. I mean, it splits any log I put on there, but it just leaks hydraulic fluid all over the place. I have to use it out in the woods. Well, I shouldn't say that. I clean up all the oil that it spills. But the limiting factor is the seals around the edge there. So now, since area 2 is big, that's a good thing. We know that it's a 5 centimeter diameter. So diameter at 2 is 0.05 meters. Area 2 is going to be pi 0.05 meters squared divided by 4. We can find that the area at 2 is 0.019635 meters squared. And so now we can find the force at 2 is going to be the pressure times area 2. These are at the same elevation. Now, what if they weren't? You know, like what if this plunger was down a little bit and this one was up a little bit? Yeah, the pressure at 2 would be a little bit lower, but compared to how big this pressure is, it really wouldn't matter. Like even if it was like a meter higher, the difference in pressure would be so small it's negligible. Relative to 6 million pascals, go up 1 meter through oil and it's going to be a loss of pressure of maybe like 9,000 out of 6 million. So we don't have to worry in this case about this being a little bit higher. We'll just assume that the pressure here is the same as the pressure there. So where did that pressure come from? Remember that this is a force pushing down on the cylinder, and that force caused as a pressure. It's like a force over an area pressurized the liquid, and now the liquid is pushing up on this second cylinder and causing a force. And so the pressure of 6.225 times 10 to the 6th newtons per meter squared. The e to the 6th means times 10 to the 6th times the area at 2 force at 2 is 12,222 newtons. So it's able to lift something pretty heavy. 100 newtons, and that's approximately 10 kilograms. So if you could push down with approximately the force of 20 pounds, 22 pounds, then that means you'd be able to lift something that's 12,000 newtons. So that's almost a metric ton of force that it could lift. And if it was something on there that's not quite so heavy, so let's say that it's trying to lift something that isn't that heavy, well, that just means that then you wouldn't have to push that hard. You wouldn't have to push 100 newtons to get the jack to go up. This is a pretty exciting example, right? To understand how force is magnified, not only by leverage, but also something as simple as changing the areas. Like it blew my mind when I started teaching fluid mechanics back in 2005. It had been a long time since I thought about all this, and I was really a little bit disturbed by an example I saw in one of the books where it had, all right, there's a guy standing on this, and it's connected to a platform, and then, oh man, I'm such a bad artist. Here's an elephant. Okay. Looks more like a camel, right? Let's say it's a camel. There's a guy, and you could lift a camel just by having the different areas. So, I mean, it's crazy. Like a mouse could lift an elephant as long as the ratio of the areas was large enough. That's pressure transmission. All right. Well, let's talk about manometry now. And manometry is a way of measuring pressure. Let's say that there's a pipe going down a road. In fact, the pipes here in Huntington are usually buried underneath the street. And so if you had a pressurized pipe and if you just punched a hole in that pipe, then water would be squirting all over the place. Like if it's just open to the atmosphere, water is going to be spraying all over. In fact, that happens a lot. That happens far more than it ought to around here, that they have water main breaks. And West Virginia American Water, who is the water company that provides service in Huntington and Charleston and a lot of other communities in West Virginia, they've recently asked for an increase in their rates. They asked for a 21% increase in their rates, and the Public Service Commission had a bunch of hearings and gathered evidence, and then I think eventually, instead of giving them permission to raise their rates by 21%, gave them permission to raise their rates by maybe 7 or 8%. But one of the really interesting things that came out during that rate increase hearing was one of the supervisors, he's like a field supervisor, so you know, like a guy who gets his hands dirty and is out in the field fixing pipes here in Huntington, said that they have water main breaks and the water company isn't able to get the valves closed to actually shut off the water. So there's probably a water main that's going down 3rd Avenue here. If there was a break in the pipe underground, then they have to scramble around trying to find a buried valve that they can close. But these valves are so old and poorly maintained that they struggle to find a valve that they can close. And there was an incident here in Huntington, a water main break on the other side of the railroad tracks, where it took them more than 24 hours to actually find a valve that was serviceable. They, I think, uncovered 7 or 8 valves before it was finally maybe the 8th or 9th valve they tried that they could force closed, because they've got to close the valve before they can go in and patch and repair the pipe. So that's a long way of saying if you've got a pipe and there's a hole in it, water's going to be spraying all over the place because it's pressurized. Well, let's say instead of letting it spray all over the place, what you do is you put a small tube and it goes up. Well, what will happen is that the water is going to rise in the tube. It's not going to keep spraying out indefinitely. It'll rise and then it will stop rising at a certain point. How do you think you can know how high the water level will rise to? When what equalizes? Okay, yeah, in a sense, yeah. It's when there's an equilibrium. And so this tube, as Andrew said, it looks like it's open to the atmosphere. So here we've got air, and here is air pressure. So we'll say that this is the pressure is equal to 0 there. And here inside the pipe, this is, pressure of the pipe. A typical value in a water network might be 500 kilonewtons per meter squared. So the water level is going to keep rising until it comes into an equilibrium. And so until the pressure of the water down from this tube is equal to the pressure of water inside of the pipe. And so the water level, the height that it rises to, is going to be equal to pressure divided by, because delta P is delta H times gamma, so delta H is going to be delta P divided by gamma. And so a piezometer is a way of measuring pressure. If you've got a really highly pressurized water pipe, then it'll rise tall. Like 500 kPa, approximately the delta H for that is going to be around 50 meters, 52 meters. Because if you've got 500 kilonewtons per meter squared and 9.81 kilonewtons per meter cubed, then the delta H will be, is it 52? Anyone with a calculator handy? How much? 51 meters is how high the water level will rise to. But if the water isn't pressurized as much, if it's only minimum conditions might be 250 kilonewtons per meter squared. If it's that much, that's enough to keep contamination out of the pipe. Any lower than that, and there's a risk that actually there could be seepage into the pipe, or that when someone on a hill flushes the toilet, it could go the wrong way. During a low pressure event, that's the risk, is that people who are at a really high point in the network are going to open their faucet, and that'll allow the water to flow into the network instead of out of the network and contaminate it. So if the pressure was low, 250, then the delta H would be around 25.5 meters of head. And they call this head when the water rises a certain distance above the pipe. Pressure and head are related. The pressure in the pipe, I guess I can just use this example. If the pressure in the pipe is 500 kilopascals, then the head is 51 meters. It's just the pressure divided by gamma has units of distance, and that's referred to as head. So. Okay, so calculate. If H is 10 meters, what will be the pressure in the center of the pipe? How could we use this piezometer as a way of calculating the pressure? Robbie, right? So what's the pressure if the head is 10 meters? Anybody get that? 98 kilopascals. Right, good. Exactly. All right. I think that's the last slide, right? Is that the last one in the notes there? All right. Well, yeah, let me just mention this final point before you go. The problem is with the piezometer is it's open to the air. And so think about if this was the way they were trying to measure the pressure in the pipe in Huntington, like if they were trying to use piezometers. Okay, so for the first thing, typical water pressure would mean that this tube is rising 51 meters above the pipe. And so people have to walk around on really tall stilts to like read the pressure, you know, or I don't know, maybe like using a surveying level to, it just would be, the height is too tall. And so that's one thing about it, it's impracticality. The other thing is that it would be a route for contamination, because if this is open to the atmosphere, then a bird that's flying overhead, you know, could get waste into the water, and so there's potential for contamination. And then this piezometer, if it was a gas that was traveling through, then the gas could just escape into the atmosphere. So in the next class, we're going to talk about different ways of measuring pressure that are an improvement on the piezometer that overcomes those weaknesses of the piezometer. I was just handing out the first lab. I didn't get through all those, so let me just leave them here on the table. You can grab it on the way out. And remember that we've got our labs today at 2 and 3. Group A, let me go back to the group assignments just one last time. Here's Group A and Group B. So no questions about who's when. I'll see Group A at 2 o'clock, Group B at 3. We'll meet at the desks. We'll have a little pre-lab discussion, and then we'll go run the experiment. See you then.